Welcome to UV Physics Academy. So here we are discussing Grover's algorithm, and in the second part we are going to discuss about the matrix representation of Grover's iteration operator. So what is this Grover's iteration operator? So this contains two parts. One is diffusion operator, another is inversion operator. That T stands for target state. So we can write this as IT equal to I minus 2 into outer product of target state, right? So keep it aside. Now, in the beginning, we have created the superposition state. Let it be psi naught initial state. How we created H tensor n operates on this 0 state. There are n qubits are there. So this is nothing but 1 over root n summation x, where x is equal to 0 to n minus 1. That means this is the superposition of all the states. Now let me split this into target and remaining states. I am taking this alpha naught initial amplitude for the remaining states plus beta naught amplitude of the target state. And remember, r is not equal to t. And alpha naught and beta naught both are equal to 1 over root n because the initial amplitudes are same. Now our aim is to find this operator, matrix form of this operator. So that's why I'm assuming this DIT operator operated n times on psi naught. Let us suppose that is a DIT operated n times on psi naught. Then we may get psi n. This psi n is nothing but, let us suppose, alpha n, these are the remaining states, and beta n amplitude of target state. Okay, and of course r is not equal to t. Don't bother about that alpha n and beta n. You may get one doubt. So here you have used the inversion operator. So why you are not getting any amplitude negative? Final answer, all amplitudes are positive only. That you will understand while I am explaining the example. So just leave it now. Okay, so let us operate one more time. If you operate one more time, that is a DIT, then what you will get? Psi n plus 1. Okay, so let it be alpha n plus 1 and beta n plus 1. So here we are going to find that amplitudes alpha n plus 1 and beta n plus 1. Target and the remaining states amplitudes we are going to find out. Okay, so how to get this as I n plus 1? The first operation is the IT. Okay, so IT is going to operate on psi n first. That is, already you know what is a psi n here. The amplitude is plus, now it will become minus. So that is alpha n, this is the remaining, minus beta n target. Okay, fine. Now I am assuming this is equal to Vn. So for algebra purpose, I have taken this. And don't forget, here Vn is nothing but alpha n summation or minus beta n target. Okay, so now I'm going to operate a diffusion operator. This D will operate on this, but we have assumed it is equal to Vn. So D operates on Vn. And you know what is the diffusion operator? So that is minus Hn, I naught, Hn, and Vn. Here I am not substituting Vn. I am going to substitute this I naught. What is I naught? Here we have already defined IT. Similar to that, we can write this as I minus 2 into outer product 0. Okay. So if I substitute this, this is nothing but minus Hn bracket I minus 2 outer product 0 Hn into Vn. Now let me multiply this. Okay. So this is nothing but psi n plus 1 finally, minus hn, just I am multiplying I hn ket vn. After that we have plus, because minus into minus plus, here 2, and hn operates on ket 0, of course n qubits, and after that bra 0, of course here also n qubits, hn vn. So here we have one matrix element, this we call it as a matrix element generally, and here again we have a superposition state. Okay, and if you see this first one, this is nothing but identity, because the h square, Hadamard square, will give you identity only. So this is nothing but identity. So minus vn plus 2 I am writing here, and this will create one superposition, that is 1 over root n summation x, summation over x into ket x, where x is equal to 0 to n minus 1, that you know already. Okay, and after that we have this Hadamard operation on a 0. So if you observe carefully, this hn operating on 0 like this, and here hn operating on this is 0 like this. Since Hadamard operator is a Hermitian operator, it can operate either on ket vector or bra vector, because hn dagger is nothing but hn. It's a Hermitian operator. Okay, so here also we'll get 1 over root n, okay, summation, but not a ket. Here you will get instead of ket we will get bra vector, so summation over x. After that into vn. Now see carefully, here we would like to find this inner product first, this product. How to get that? So let me write this again. Here finally we got psi n plus 1 equal to minus vn plus, and here we have 2 by n summation over x ket x plus, again actually there we have 1 over root n, 1 over root n, just I have written n outside, and after that here we have summation bra vector of x and this vn. Okay, let me check. Yes, absolutely fine. Okay, now I hope you know what is this vn. Vn is nothing but alpha n summation, and this is r, not plus, because already inversion operator taken place. That's why this is a minus beta n into target. So here we would like to find this inner product. That's why better to split this x into remaining and a target. So I think this can be written as a summation, okay, and this is the remaining plus, because here there is no inversion operation, it's a just a superposition. So plus, this is the target. Already 1 over root n you have taken here. If you have any confusion, I will take one more like this, then you will understand. Okay, so that's it, and now I'm going to multiply. So I'm going to multiply here, and one small thing, please carefully observe, here we should not write ket vectors. So this is nothing but summation bra vector of r plus bra vector of t. Okay, already here 1 over root n is there. Fine, and don't forget how many remaining states, n minus 1. Now I'm going to rewrite this minus vn plus, here I'm taking n root n into root n, that is n, and this summation is as usual, I'm not disturbing it, and I will write this x again, just wait. After this what we have, just we are going to multiply this. So then you will get summation alpha n into 1, that is alpha n bra r into ket r minus beta n bra t into ket t. I hope you got it. So here we have how many terms, I mean this inner product will give you 1 and this inner product will give you 1. But I request you, this summation is not for beta n, only for this one. Okay, please take care of it. And here how many terms are there? Here we have n minus 1 terms. That's why finally we can write minus Vn plus 2 by n summation over x. Now carefully see, here I am writing this x ket vector, and now whatever the constant I have that I am writing, summation gone already because n minus 1 terms are there. So summation over n, summation 1, because n minus 1 terms are there. So this is n minus 1 into alpha n minus beta n. That's it. Okay, so I can write this yeah, n here. That means I'm rewriting this minus Vn plus 2 outside only, the summation over x. Here I am writing 1 by n minus 1 alpha n minus beta n. Okay, so this one will define it as average amplitude. So this one I'm defining as average amplitude, that is an. This is very important, don't forget. So finally we can write this as minus Vn plus 2, and here we have this summation over x, and this is an x, where this an equal to, this is a very important, average amplitude after n number of iterations, 1 by n minus 1 alpha n minus beta n. 1 by n is common to both. This is what we get. Okay, so right, so let me write this the next page again. So finally this is the result we got. Okay, this is the average amplitude after n number of iterations. And now what I'm going to do is I'm going to substitute what is Vn here. So here we have minus Vn, that's why minus alpha n summation remaining states minus of minus plus beta n into target. Okay, so after that plus 2, here we have summation, of course here we have an, and again here I'm going to split this. So I'm going to split like this, 2, and after that an, the summation x, that means the sum of all the states. I'm going to split it as a target and remaining, so that's why summation remaining plus target, where r is not equal to t, and here also r is not equal to t. Now I'm going to combine these two expressions, then I will get, if you observe carefully, 2an minus alpha n summation, these are the remaining states. Next after that, for target, 2an plus beta n into target state. So if you observe carefully, the amplitude of the remaining states decreased and the amplitude of target state is increased. Here if you observe carefully, here plus and here minus. And we can represent this thing is nothing but alpha n plus 1, because n plus 1 iterations completed, and this one I am taking it as a beta n plus 1. Okay, so here what happened, let me substitute alpha n plus 1 equal to 2an minus alpha n. Let me find this. So 2an already we defined, 2 by n into alpha n minus 1, okay, minus beta n. Just to split it. So this is nothing but alpha n common. I'm taking common. So 2 will be there because n by n cancel, minus this is a 2 by n minus uh, 2 by n beta n. That's it. Okay. And after that, so what about this beta n plus 1? So this is a 2an plus beta n. So just substitute an here. This is a 2 by n alpha n into n minus 1 minus 1 by n into beta n plus beta n. But here we are multiplying with the 2, so that's why here also you'll get a 2. So how can we take the common here? Alpha n common, then n gets cancelled. So this is nothing but a 2 minus 2 by n. I think some mistake is there. Wait a minute. This is nothing but plus 1 minus 2 by n into beta n. Let me check here. This is the mistake, I think. Yeah. So here we forgot to write this minus alpha n. Okay. So once you have taken that minus alpha n, and there is a small change here, otherwise one more extra term. So this is a minus 1, sorry. Minus 1. So then this is nothing but alpha n 1 minus 2 by n minus 2 by n into beta n. That's it. So here we got beta n plus 1. So finally we can represent this alpha n plus 1 and beta n plus 1 in the matrix form. So finally we will get alpha n plus 1. Let me write in the matrix form. Alpha n plus 1, beta n plus 1. These are the amplitudes of a remaining and a target state after n plus 1 iterations, and we will get this 2 by 2 matrix, and here we will get alpha n beta n. If you write these two equations in the matrix form, here you will get first element 1 minus 2 by n, you get 1 minus 2 by n, and here minus 2 by n, and here 2 minus 2 by n, and here 1 minus 2 by n. So that's it. And here we got this iteration matrix. So 1 minus 2 by n, minus 2 by n, and 2 minus 2 by n, and 1 minus 2 by n. So that's it. And finally, that means what we have done here one more time. Let me explain. Here our aim is to find the matrix form of this iteration operator, that is a DIT. So first I assumed that superposition state as usual, and I assumed in a number of times it is already operated on psi naught, and I got psi n with amplitudes alpha n and beta n. And one more time I have done this iteration. So first inversion operator, then we got minus beta n there, and I assumed that state as Vn for algebra purpose. And the next diffusion operator is operated on Vn, which is nothing but psi n plus 1. And some small algebra is there. Okay. So here the head mod operator is the Hermitian. So that's why we got that ket vector and bra vectors superposition state. And after that, we have some inner product here. So that's why I split this X as a remaining and a target states. Okay. So once you have taken this summation, one more, don't get confusion with these two summations. Okay. So both the summations are same only, no need to worry about that, because the summation is related to this X only. Just we are splitting that remaining and a target states. That's it. And some small inner product is there. And finally, we got this amplitude. This is the average amplitude after n number of iterations. Let it be an. And after that, we substituted vn. Okay. And I taken some common. And finally, we got this state, which is a psi n plus 1. And this amplitude is a amplitude of remaining states after n plus 1 iterations. Let it be alpha n plus 1, and this is the amplitude of target beta n plus 1. Then the small algebra. Okay, so simple. And after that, we just represent that linear equations, two equations we got in the matrix form. Then this is our iteration matrix. So finally I can say this dit is nothing but 1 minus 2 by n minus 2 by n and 2 minus 2 by n and 1 minus 2 by n. That's it. It's very nice. Okay, fine. And we'll meet again in the next lecture, and there we will discuss the circuit design of Grover's algorithm. Okay, thank you.